Lucía Menéndez-Pidal, The Problem of Time in Quantum Cosmology from Different Perspectives. Thank you.
Thank you. Okay. Thank you very much. Thank you very much for allowing me to speak in this session. And yes, I will talk about the problem of time from different perspectives, namely the canonical quantization perspective and a little bit of the path integral quantization perspective. So I have given similar talks in the past, but I will try to tell it in a slightly different way. So yes, we're going to work on the problem of time in a cosmological toy model, and my toy model is basically a flat FLRU universe. Instead of working with the scale factor A, I will work with the scale volume, which is proportional to A cubed, just because it was simpler mathematically. And the matter component of my model is a massless scalar field, and a bit the spicy component of my model is a cosmological constant, but this cosmological constant comes from unimodular gravity a la Tater-Boym. So instead of being a simple plain cosmological constant, it comes with its conjugated coordinate. But for the purpose of this talk, the only thing you need to know is that I have a toy model that has 3 pairs of canonically conjugated variables. One of them is T and lambda. This lambda is my unimodular gravity cosmological constant. One pair is my scalar field phi and its conjugated momenta, and the other pair is my scale volume, which is defined to be positive, and they're all canonically conjugated. We can write the Hamiltonian of our system, and it has this expression where n here is the lapse of the metric. And because this is a totally constrained Hamiltonian, we have to set this constraint equal to 0. And we can see that it's a function of the variable of my model. And this model is a cosmological model that has a big bang and a big crunch singularity. So now we want to quantize this. And we can quantize it in the gauge n tilde equals 1, in which we have this constraint. And we can obtain the Wheeler-DeWitt equation. Well, we will quantize the model using the Wheeler-DeWitt equation. And in this case, if one ordering or one way to obtain a Wheeler-DeWitt equation from this constraint is to go from here to this equation, in which the important part is that I have a ddt term here. So basically, if I take this operator and I put it on the other side, what I find is a Schrödinger equation in T. So this Wheeler-DeWitt equation is suited to use this parameter T as a relational clock to express how the rest of the variables of my model vary. However, we can also choose to quantize this model in a different gauge, namely taking n tilde equals v squared. So instead of having this constraint, we have the same constraint but multiplied by v squared, and we would obtain the same Wheeler-DeWitt equation, but this time multiplied by v squared. And this Wheeler-DeWitt equation is nice because now we have a second derivative with respect to phi, so if I move everything else on the other side, I have sort of a Klein-Gordon equation in phi. So far, these Wheeler-DeWitt equations have the same solutions because one is only v squared times the first one. Therefore, there is some sort of covariance in the quantization. But if we do the further step of the quantization, we will see that things start happening. Namely, let's take the theory that we call the T-clock theory, which is where we chose the n tilde equals 1 gauge. If we want to build a Hilbert space of this theory to see how observables evolve, what we find is that dynamics are governed by a Schrödinger equation of this type, in which H is an operator that depends on the rest of the variables of our model. And our Hilbert space is defined by this inner product, which is an integral over V and phi. To ensure unitary dynamics, we need this H, this Hamiltonian, to be self-adjoint. However, the Hamiltonian is not directly self-adjoint, but admits a family of self-adjoint extensions that are parameterized by this boundary condition. The only thing you need to know about the boundary condition that I'm showing here is that it is a reflection around v equals 0. And I should point out that as v is the scale factor cube, v equals 0 is the point in where classically we have the singularity. And so this boundary condition leads to singularity resolution, as we can see in this type of plot. Here I have plotted V as a function of t. The black line is the classical solution, and the dotted lines are quantum expectation values of V as a function of t in this quantum theory for semi-classical state, and the differences between these two curves are only different choices in the free parameters we had. And we can clearly see that instead of reaching V equals 0, the quantum theory, or quantum expectation values, never reach V equals 0 and exhibit some bouncing behaviors. However, we can work in the other theory in which we had the DeWitt equation that we obtained from a different classical gauge, and this time the dynamics are governed by the Klein-Gordon type equation, and we have a Klein-Gordon type inner product, but we have the same issue, that our evolution operator has to be self-adjoint, and it's not self-adjoint initially, rather it admits, once again, a family of self-adjoint extension parameterized by this boundary condition, which looks exactly the same than the one I had before. However, this time, instead of being a reflection around V equals 0, it's a reflection around V equals infinity, which is the spatial volume of my universe. So this boundary condition is going to lead to something that we called spatial infinity resolution, as we can see in this plot. This time, I plotted V as a function of phi and also calculated the same quantum expectation values. And here we can see that the quantum expectation values, instead of going to infinity, they reach a maximum that is finite, so my universe expands and then recollapses. So in the canonical theory of this toy model, we have seen that to ensure unitary evolution, one must impose additional non-trivial boundary conditions, and these different choices of laps that classically do not, or my theory classically is covariant, so the choice of laps doesn't matter, but here the choice of laps lead to different boundary conditions, and the dynamics, in particular singularity resolution, are affected by these kind of choices. So don't leave just yet, because I have more. So the first thing we thought is that the canonical theory seems to be non-covariant, and we have this unitarity issue. What happens if now I want to analyze the same toy model, but from a different perspective? The path integral quantization formalism is supposedly covariant, so the question we ask ourselves is how to analyze this problem in the path integral formalism, and what happens to unitarity and these boundary conditions. So just a recap of what path integral quantization is very loosely. So it is sort of a probability of going from an initial to a final configuration, and in this type of models, because we are a universe, the final and initial configurations are usually given by the metric, or if you have extra matter, well, the extra matter, no? And this is done by doing a functional integral over the metric and the matter degrees of freedom weighted by the Einstein-Hilbert action, right? So how do we do this in our model? So path integrals in cosmological models have been analyzed, and typically they have this kind of form. So in our model, we have, remember, we have three variables: my volume, my field, and t, which is related to the cosmological constant. So my path integral would be a function of a final configuration and an initial configuration of the functional integrals over the variables, my canonically conjugated variables, the coordinate and the momenta, weighted by the classical actions. I have to add extra terms here that are made to make this integral gauge invariant. In this setting, gauge invariant means in covariant under the change of laps. So I can write my theory in the T-clock theory gauge, namely n tilde equals to 1, in which I would have this action here, in which see that what is under the bracket is the first constraint I have, but I could equally write my action with the other gauge we analyzed, which is basically the gauge in which the constraint has this form, and this action, without specifying, without explicitly calculating these terms, because of this, is covariant or invariant under this change of gauge. And well, when doing this path integral, we could simplify one of the functional integrals, but in particular the integral with respect to v is very hard to find an expression for it, because v is defined only on the half line. So we encountered some problems, namely that finding an analytical expression of this is very hard. So we thought, okay, we have a canonical theory. Typically in quantum mechanical models, people can relate the canonical theory to the path integral quantization, and they do so by these kind of formulas, in which you have your probability or amplitude, and you write it as an integral of this E would be the energy of your system, of the eigenstates of the energy associated with your canonical theory. So here this phi E would be energy eigenstates of my canonical theory. But in our case, we had two different canonical theories, so that correspond to two different choices of labs. So what is going on? So there are a few ways of treating with these models in which you don't have a self-adjoint Hamiltonian, namely not very easy, but the first toy model we looked at is the free particle restricted on the half line, for which the Hamiltonian is not essentially self-adjoint. And what they do here is that to relate the path integral to the canonical theory is that they add boundary terms, they incorporate boundary terms in the path integral, so they add some extra terms. But in this simple model, simple canonical quantum mechanical models, they don't have this lapse issue, so it is always clear which boundary terms they have to add to the path integral. In our case, these boundary terms would depend on the choice of lapse that we made in the canonical theory. So in the end, we lose again covariance. So to conclude, this is very much work in progress, so I don't have all of the expressions and stuff, but I just wanted to show you this because I thought it is very interesting. So what have we seen in this talk? How in a simple model, different lapse choices affect the result of the canonical quantum theory by introducing extra boundary conditions, and these extra boundary conditions ensure unitarity, but we break covariance. And how this loss of covariance is also manifest in the path integral formalism, because at the end, if we want to take into account unitarity, we need to add these boundary terms that again depend on the lapse, so we kind of lose the lapse covariance that we had initially. And what we want to do in the future is to have a better understanding of the boundary terms that appear in the path integrals and do further calculations in this model. So, yes, thank you.
Thank you very much, Lucia. Questions?
Thanks for the nice talk. So at the beginning, you showed us a plot for the expectation value of V and how it resolves the singularity. How large are the fluctuations of V at this point?
You mean here, right?
Yes.
So they are larger than here. I have some of the calculations in my thesis. For these two specific cases, I don't know, but it's true that they can be quite large.
Yeah, I just mean
so
like,
there is some uncertainty going on.
Right.
There.
So is it okay to like truncate to just the expectation value, or you should look at higher moments? I mean, we need to take into account higher moments as well near the singularity.
Yeah. So you should take this value with a pinch of salt, no, because the uncertainty can be quite high. But you can certainly have cases in which the uncertainty still gives you something strictly above 0. Yes. But they will depend on because these are semi-classical states, on the parameters of the semi-classical states.
Okay, thank you. I think it's time to thank all the speakers and the final speaker for their nice presentations. And we will have the ice cream now, and we reconvene at 4 o'clock. Thank you.